Alrighty, lads and ladies, welcome back to the party. Today we are going to continue talking about what we introduced last Friday, which was this concept of a parametric curve. I'm going to go through the sort of formal definitions. We're going to treat this a little bit more formally today than we did on Friday, and of course we're going to go quite a bit deeper. A few comments. I don't think this actually applies to anybody who's in the meeting right now, but there were a few people who did not submit written work for their test. And without that written work, if you're watching the video or anything like that, I just want you to know, without that written work, the best I can do for any of the free response questions is 2 out of 10 points. And that assumes that your answer is correct. So if you did not submit the written work, I really need you to do that. If you have the scans from that day or photos you took from that day, I can verify through the metadata that those are the originals, and I would be happy to regrade your work with that. Just send it to me as quickly as you can, please, because otherwise those scores are going to be quite low. All right. So this is MAC2312, section number 004, which is a Calc 2 class, and the date today is the 6th of April, 2022. As we near the end of the course, there are only a few topics that remain. And like I said, today we're going to go full hog into parametric curves. This is section 10.1. There's a chance that we'll get into a smidge of 10.2 today. Let me add that here. 10.2 is just calculus with parametric curves. Section 10.2. As we discussed last Friday, a parametric curve is, we said, this is a curve where x is not necessarily a function of y is not necessarily a function of x, but both x and y are functions of some third variable, which we call the parameter t. So this is the set of all points x of t, comma, y of t in the plane where t runs from some value, I'll call it a, less than or equal to t, less than or equal to b. So your x values, your x coordinates on these points are functions of t. That's why I'm writing x of t here. And y is also a function of t. This is kind of a terse definition, but it is the definition. We're going to look at some examples where we graph these. We've done a couple of them. I'll pull up some more from your textbook here, so we have a nice wealth of them. And then I want to talk about how to find parametrizations, how to reverse parametrizations, things like that. So this example we have not done. Let's go ahead and do this. T squared minus 2t and t plus 1. What was y here? Was t plus 1. Did they specify a time domain? They did not. So let me say t is going to run from we'll specify a time domain for this guy just as we warm up. If you're trying to draw a curve and you have the equations that define the curve, just like you did back in middle school, the only way to approach this, unless you have some more sophisticated tools, is by making a table. And there's nothing wrong with making a table. It's where we always start when we're thinking about stuff like this. Tables here are going to be one column for t, one column for x, and one column for y. And each row of the table will give us a point on the curve. All right, so just like how you made your X and Y tables back in 8th grade, we're going to make T, X, Y tables here. T is allowed to run from -2 to 4. And so I'll just use some of the integers in there, like -2. Maybe I'll -1, 0, 1, 2, 3, and 4. Use all the integers. And then to find the point on the curve associated with t equals -2, we plug -2 in here. That'll give me the x coordinate. Plug -2 in here. That will give me the y coordinate. So if I plug -2 in for the x equation here, I get -2 squared, which is 4, minus 2 times -2. So that's 4 minus -4 is 4 plus 4 is 8. And if I plug t equals 2 into here, 2 plus 1 is 3. Oh, sorry, -2 plus 1. -2 plus 1 is -1. All right. If I plug -1 in for t in the x equation, I get -1 squared minus 2 times -1. That's 1 minus 2 times -1. 2 times -1 is -2, so that's 1 plus 2. That is 3. And if I plug -1 in for t here, the y is going to be 0. If I take this t value, t equals 0, and I plug it into the x equation, I get 0 squared minus 2 times 0. That's definitely 0. And 0 plus 1, when I plug into the y, is going to be 1. If I plug t equals 1 into the x equation, I get 1 squared minus 2 times 1. That's 1 minus 2. That is -1. And when I plug t equals 1 into the y equation, I get 1 plus 1, which is 2. Keep going like this. If I plug t equals 2 into the x equation, I get 4 minus 4, which is 0. And if I plug t equals 2 in here, I get 2 plus 1 is 3. If I plug t equals 3 in here, I get 9 minus 6, which is 3. And if I plug t equals 3 in here, I get 3 plus 1, which is 4. Finally, if I plug t equals 4 in here, I get 16 minus 8, which is 8. If I plug t equals 4 in here, I get 4 plus 1, which is 5. So each row of the table gives me a point on the curve. But my y value is going to go from -1 up to 5. So we'll do something like this. And my x values are going to go from -1 up to 8. So I'll mark this as 8. I should make this about 2, 6. So here, so -1 here, 7. My y values go from -1, which I'll mark here, up to +5. So 1, 2, 3, 4. All right. So I've got some coordinate axes. I just need to plot some points. We start with the point 8, -1. And this is my initial point. It's the point where my curve starts. When t is -1, we're at the point 3, 0. That's right here. When t is equal to 0, we're at the point 0, 1, which is right here. When t is equal to 1, we're at the point -1, +2, that's right here. When t is equal to 2, we're at 0, 3, which is right here. When t is equal to 4, we're all the way back out at 8, 5 here. So if you connect these dots with a nice smooth curve, you got some fresh colors today, you will get something looking like this. Which is a shape that should look familiar, modulo my bad art. This looks like a parabola, right? It's on its side, that's okay. This was my initial point. Remember the name for the point where your curve starts, the point associated with the smallest t value. It's called the initial point. The point where your curve stops, the point associated with the largest t value, we call the terminal point. And here that's the point associated with t equals 4. That's the point 8, 5, and it's associated with the t value, t equals 4. So as t increases from -2 up to 4, I'm walking along this curve in this direction. Remember, the arrows indicate what we call orientation. You can think of this curve as being a path, like there's a little ant in the plane. He starts out over here when t is equal to -2, and he's just walking along this curve. Because he's walking along the curve, there's a direction to that, and that direction is what we call the orientation. Which is the direction of travel along the curve. So the first big goal in section 10.1 is just this, right? I give you some parametric equations. You draw me the curve. You need to make sure you can label the initial point, the terminal point, and draw the arrows for orientation correctly. Are there any questions about how I came up with this graph? Okay, I want to revisit this thing. I think we did talk about it a little bit last week, called eliminating the parameter. So let me remind you what we can do there. We can also graph a parametric curve. And eliminating the parameter is what it sounds like. It means get rid of t. Find me some normal x, y equations for this that don't involve the variable t. So let's eliminate the parameter for this parametric curve and see if we can't come up with this guy without making a table. That's our kind of next step here. Just like how in your algebra classes of yore, you started by making tables to plot curves, but then eventually you learned enough about curves and transformations, things like that, in order to graph these without making a big old table. The way we would do that here, and sort of the standard way to do this, you write down your parametric equations. When I do this, I don't write the of t, I just write x, so x equals t squared minus 2t, and y equals t plus 1. And you solve one of the equations for t. Now here, it's easier to solve the y equation for t, so I'm going to do that. This would mean that y minus 1 is equal to t. And then plug t equals y minus 1 into the other equation, to the x equation. So you solve one of the equations for one of the variables. So solve one of the equations for t, sorry, and then plug that into the other equation. So that will give me x equals y minus 1 squared minus 2 times y minus 1. There's a few things we could do with this from here. I can get to the factored form pretty quickly by factoring out a y minus 1. That will give me y minus 1 times y minus 1 minus 2, which is y minus 1 times y minus 3. So from this, you can see that your curve, that the normal xy equation is x equals, it's the factored form of that quadratic, y minus 1 times y minus 3. And from here, we could graph the curve. This up a little bit. That y minus 1 tells me I have a y-intercept here when y is equal to 1. And the y minus 3 factor tells me I have a y-intercept when y is equal to 3. And we know that the only curved quadratic function of y that could do that is a parabola opening sideways, like so. And that is what we had. Well, what this picture does not have is the initial point, the terminal point, or the orientation. So to find the initial point, terminal point, and orientation, plug the smallest and largest t values into the parametric curves, or parametric equations. So basically, you still have to calculate the top row of your table and the bottom row of your table. The smallest t value we had was -2. And if you plug -2 into the x and y equations, you get -2 squared, which is 4, minus 2 times -2. That's 4 plus 4 is 8. So the x coordinate there is 8. And when you plug -2 into the y equation, you get -2 plus 1 is -1. So I can label this point, we'll do it right here. It's 8, -1, and that's our initial point. And when you plug the largest t value you have in here, what was that, 5, right? You'll have 5 squared minus, was it 5? Might have been 4. 4, yeah, sorry, t equals 4. So plug in here, we get 4 squared minus 2 times 4 is 16 minus 8, which is also 8. And when you plug t equals 4 in here, you get 4 plus 1 is 5. So I can label this point up here as 8, 5, and that's my terminal point. So all this tells me that the portion of this parabola that I was able to find by eliminating the parameter, the portion of this parabola that is actually my parametric curve is the stuff between the initial point and the terminal point, which is the stuff I'm highlighting in blue now. And then the orientation, you have to travel from the initial point to the terminal point. So that means we have to be traveling like this. Orientation can be a little bit more subtle than that sometimes, and we're going to look at some problems like that. We're going to revisit that ellipse problem from last Friday. But I want to make sure we're comfortable with this kind of simple example here. So are there any questions about how we get this curve, the picture here, by eliminating the parameter rather than making a table? Okay. Let's try this again. This time, we did the unit circle on Friday of last week. So let me play with that just a smidge. So let's sketch the parametric curve. X of t equals 3 sine t, y of t equals 3 cos t. And we're going to allow t here to run from 0 to 3 pi over 2. This is slightly different than the circle or ellipse example that we did last time. We're going to get to the same sort of result though. And we're going to do this by eliminating the parameter. We're not going to make a table. So if you want to see an example like this where we make the table, you can take a look at the video from last week. Does anybody remember the trick for eliminating the parameter when your x and y equations, instead of being nice algebra equations, are like trig equations, specifically sines and cosines? Anybody remember that? We have this identity, right? This trigonometric identity, which is very useful for problems like these, and will be very useful when we're talking about polar coordinates as well, which we're going to be doing in sections 10.3 and 10.4. Sine squared plus cos squared of anything, sine squared t plus cos squared t, sine squared yo mom plus cos squared yo mom, always going to be 1. So just like we did before, I'm going to write down the x and y equations without the function notation. I'm just going to write x equals 3 sine t. And then I'm going to square both sides. This means that x squared is 3 times the sine of t all squared, which is 9 sine squared t. All right, 3 squared is 9, sine t squared is sine squared t. I'll do the same thing for y. Y was 3 cosine of t, which implies y squared is 3 cos t all squared, which is 9 cos squared of t. So if I add these up, if I add x squared to y squared, then I'll get 9 sine squared t plus 9 cos squared t. Oh yeah, I'm sorry, I didn't see that. That's correct, yes. So if I take now x squared plus y squared, that's going to be 9 sine squared t plus 9 cos squared t. You can factor out the 9, and you have sine squared t plus cos squared t. And since that is 1, this is just 9 times 1, or 9. So in other words, the equation, the normal xy equation for this curve is x squared plus y squared equals 9. We have eliminated the parameter. This is a circle centered at the origin with radius 3. Remember, x squared plus y squared equals r squared is your circle at the center of the origin of radius r. So I know that the graph is a portion of, right? Like we didn't get the whole parabola last time, we just had from that one point to that other point. Similarly here, I'm not necessarily expecting to get the whole circle. I know this graph is a portion of the circle. So let me draw that circle. And then we're going to figure out what part of the circle we have and the orientation with which we are going to traverse that circle. I'll come up here. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. I'm going to do the same thing we did on the last one, where I'll trace the full curve in purple, and then I'll highlight the portion of it centered at the origin, centered at 0, 0. So here's that circle. Use your imagination, pretend it's a perfect circle. I need to find my terminal point. I need to find my initial point, and I need to find the direction that I'm walking from the one to the other. Let's find the initial point. T here was running from 0 to 3 pi over 2. So my initial point comes from t equals 0. Comes from the smallest t value in your interval. X of 0. So this will be the point x of 0, comma y of 0. Zoom out. Really? Right. X of 0 is 3 times the sine of 0. So that's 3 times 0, which is 0. Y of 0 is 3 times the cosine of 0. That's 3. So my initial point is the point 0, 3. This time we're starting up here. My terminal point that's going to come from my largest t value, which is 3 pi over 2, right? Largest t value is 3 pi over 2. So that's the t value that gives me my terminal point. If we plug 3 pi over 2 in for t in these equations, the sine of 3 pi over 2 is -1. So this is 3 times -1, which is -3. And the cosine of 3 pi over 2 is 0. So my terminal point is the point associated with the largest t value, which is 3 pi over 2. So that's going to be the point x of 3 pi over 2, comma, y of 3 pi over 2. X of 3 pi over 2 is -3. Y of 3 pi over 2 is 0. -3, comma 0 is right here. Now, fun question time. Where is my curve? My parametric curve, is it this? I can go from the initial point to the terminal point by going like that. I could also go from my initial point to my terminal point by going like that. Which one is it? There was a good question there. Do we need a table to answer this? You could answer it with a table. In fact, you could answer it just by plugging in maybe 1 or 2 other t values. Just find a couple points on the curve. If they're in here, then you're going like this. If they're somewhere over here, then you're going around like this. But there's a better way to answer the question. And this is kind of what I want to get us thinking about. Let's look at this x equation, right? All the points on this curve have x coordinate 3 times the sine of t. As t goes from 0 towards 3 pi over 2, specifically close to 0, is this thing, sine of t, 3 sine of t, is that increasing or decreasing? If I look just at the x equation on its own, so here, this is the x-axis, this is the y-axis. If I look at the xt plane, in other words, if I graph x equals 3 sine t, you know what that looks like. Right? Looks like this. This starts off increasing, which means the x values on the parametric curve start off increasing. So let's come back here now. I know that my initial point is this. If I was walking like this, from my initial point to my terminal point, going along this way, would those x values be increasing or decreasing? As I go this way from my initial point, yeah, the x values would be decreasing, right? X gets smaller as you go this way. X gets bigger as you go this way, smaller as you go this way. So this means the point starts off moving to the right, which means that my parametric curve has to be going like this. Starting at that initial point, moving to the right. Now past this point, they turn around and start moving to the left. That's because this function turns around, right? This function goes increasing, then decreasing. Here my x values are increasing, here my x values are decreasing. So the orientation, this is the part of the circle that I'm getting from these parametric curves or parametric equations. And the orientation is like this. And one of the suggestions was, could we get this by making a table or something like that? Yes, you could. But my goal is to get us away from making tables and towards doing this, which is quicker. We eliminate the parameter, and that allowed us to draw the purple circle. We found our initial and terminal points, boom, boom. And then to sort out our orientation, we just noticed that the x equation, which is 3 sine t, is increasing for t values near 0. This function starts off increasing, which means the x values need to start off increasing. In other words, this point is moving to the right at first. We're going to dig deeper with this. Increasing and decreasing are concepts connected to derivatives, and we will talk about the derivative of the x function and what that tells us, the derivative of the y function and what that tells us. Yes, another DM came in. So if the x equation is increasing, that means the point on my parametric curve is moving to the right. And if the x equation is decreasing, that means that the point on the parametric curve is moving to the left. That's correct. You can also play this game with the y equation, right? If the y equation is increasing, that means your point is moving up in the increasing direction of y. And if your y equation is decreasing, that means your point is moving down. That wouldn't have been helpful here because whether you go to the right or to the left, the point is moving down. So in this case, it was more informative to look at the x equation. But there are instances where thinking about the y equation would be helpful as well. All right, questions about how we got the blue curve here with everything, initial point, terminal point, orientation arrows, without ever touching a table. Good stuff, right? All right, let's take a look at some other examples from your textbook. Let's see, I'd like to, circles. This is a fun one. What bounds for t did they give us? Let's say from, let's do like this. Let's say, describe the motion. So here what I'm going to be thinking is that this is like a particle moving along the curve, and I want to describe the motion of that particle. I'm going to think of the point x of t comma y of t as a moving point along the curve, and I want to first sketch the curve and then see if we can describe what's going on here. I'm going to add a little note. If no t interval is specified, we assume that t runs from negative infinity to infinity. We could start making a table. That's an option. But especially because we weren't given a time interval, because t here is allowed to be any real number, it's hard to decide what to put in for t values in your table. So this is another case where eliminating the parameter is the way to go. In this case, I think the nicest way to get there, again, I'll just write x equals sine of t. And I'm going to leave him alone. I'll write y equals cos squared of t. And we could use sine squared plus cos squared equals 1 again. Now there's already a cos squared here. But if I square the x, then I get x squared equals sine squared t. So adding sine squared t, which is x squared, to cos squared t, which is y, I get x squared plus y equals sine squared t plus cos squared t, which is 1, i.e., we're on the curve x squared plus y equals 1, which is the same as saying, now I'll solve this for y equals 1 minus x squared. So this is the curve that we are trapped on. And that curve, is also a parabola. This is a parabola opening down the vertex at 0, 1. And something like this. But we're definitely not going to get the whole curve here. What is the largest that sine t ever gets? Let's stay over here because t runs from negative infinity to infinity. There is no initial or terminal point. But yeah, the largest sine ever gets is 1. And the smallest sine ever gets is negative 1. And sine t, that is x. So x is always bounded between negative 1 and 1. Well, I don't have an initial or terminal point. I know that the portion of this curve that I am fucking with here is the stuff where x is between negative 1 and 1. So this stuff, we're getting washed out contrast wise here. Let me try to fix the colors for you. Stand out a little more. this part. Again, this is the x-axis. This is the y-axis. And we know that because sine is bounded between -1 and 1, and x is sine t, the x values are bounded between -1 and 1. So my parametric curve is the portion of the purple parabola that has x's between -1 and 1. What is the motion, though? What is this particle doing? Is it going to start over here and walk over here? Is it going to start over here and walk over here? Is it going to start up here, go over here, and then down over here? Again, you should think about what this equation, x equals sine t, does as t goes from -infinity to infinity. X of t equals sine t has outputs which bounce back and forth from -1 to 1. So what my particle is going to do is it's going to move over here, and then it's going to turn around and bounce back over here. It's going to come over here, and then it's going to turn around and bounce back over here. We're going to boink, 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 bounce back and forth along this portion of the parabola. That is the motion. Our point bounces back and forth from -1, 0, and 1, 0 along the curve y equals 1 minus x squared. That's t over tangent of -5. That's what's going on. And I have a Desmos tool that I put together to help you guys illustrate and see these things. Let me pull up Desmos for you. This is funny as hell, by the way, if you haven't seen this. Bounces. Point bounces back and forth. Here. I'll make one for us. So X of 2, 1, 2. Oh, it's not going to play nice, is it? No, it's not. We gotta do this a little differently. Yeah. So I can type it as an ordered pair, sine t, cos squared t. I will say 100. That's enough. And then if I want to get the point here, I have to introduce another parameter. So you can watch this. Ooh, let's slow that down. How about -5? Right? Just bounces back and forth. The whole curve is y equals 1 minus x squared. But we're not traveling over the whole curve. We're just traveling over that portion. So the red is your parametric curve. And there is no clear way to define orientation here because this goes back and forth over the curve many times. There is no initial or terminal point here because t is allowed to run from -infinity to infinity. I put -100 to 100 or -5 to 5. The idea is at this point, we'll just bounce back and forth here forever. This says x of t equals sine t has outputs which bounce back and forth from -1 to 1. All right, we have time for a few more. Using graphing devices is not very exciting. The cycloid we promised to do. Yeah, so let's cook up the equation for the cycloid. Okay. Let me do it like this. Let's go out to something like 8 pi. The geometry involved, the way the book does it is they tell you what a cycloid is, and then they ask you to cook up the equation for the cycloid. What you should imagine here is a little wheel rolling along the ground, and we're going to track one point along that wheel. So what I'm doing here is a cycloid with a radius r equals 2. Rather than dragging you through that procedure, let me show you what's going on. So here's our x-axis, here's our y-axis. What you imagine again is a wheel of radius r that is rolling to the right, yeah, like you see here. And then the point P on the curve is is a fixed point on that wheel that we're going to follow. Turn this on for a second. Have you ever seen a bicycle go by with lights on the wheel? It makes this path like this. That is a cycloid. And the result here, something that looks, I'm trying to chalk this up. So this would be if the radius is 2. Something. So this. Each one of these loops here corresponds to a full rotation of the wheel, which would be 2 pi. So this would be the point associated with t equals 2 pi. This would be the point associated with 4 pi. Let me just change this to a 4 to make our lives easier. So this would be the cycloid of radius 2, meaning this the wheel that's rolling, it's of radius 2. So this height here would be 4. And this horizontal distance here would be the circumference of the circle of radius 2, which is 4 pi, 2 times the radius. And these are y values up here, and this is an x value down here. And this would be 8 pi. So as t goes from 0 to 4 pi, x goes from 0 to 8 pi. Because it is a cycloid, we're tracing out this sort of pattern. The place I want to go with this is not so much can you come up with this geometry. It's if you have this picture, can we find the mins and maxes? This max. This max. This min. And the way I'd like you to get there is by thinking in the fashion that we were thinking a moment ago when we tried to find the orientation for our circle. We said we can think about the x function as starting off increasing, which means our point starting off moving to the right. Let's think about the y function. If the y function is increasing, that means we're moving up. If the y function is decreasing, that means we're moving down. You know that to find mins and maxes, what we want is the normal Calc 1 derivative dy dx. If dy dx is equal to 0, then you have a critical point. If dy dx is undefined, you have a critical point. Those are places where you could have mins or maxes. I'll say we may have extrema. Remember, extrema is the word for min or max. So this is a theorem. And it works exactly how you would hope it works, given parametric equations. X equals x of t and y equals y of t. Dy dx is, think about kind of dividing top and bottom by dt. It's not 100% kosher because dt is a differential, not a number, but it works out just fine. It's really a consequence of the chain rule. I could calculate dy dt as dy dx times dx dt, and then divide both sides by dx dt. And there is an alternate notation for this. If you don't like writing all the dy dt, dx dt stuff, this is a notation that comes from physics. Sometimes we just write y dot for dy dt and x dot for dx dt. Either notation is fine. So what I'd like to do is compute this dy dx for the parametric curve up here, the cycloid, and see if we can't locate these points. Let's do it. This is a piece that you want to hold on to. So I'll rephrase the question. Find the location x comma y of any mins or maxes along the cycloid x of t equals 2t minus sine t, y of t equals 2 times 1 minus cosine t. To get the normal dy dx slope of the tangent line derivative, you need to calculate dy dt, you need to calculate dx dt, and then form this ratio. I'll use the Leibniz notation. Dy dt. That means I'm going to differentiate this with respect to t. The 2 is a constant multiple. It will come along for the ride. 1 will differentiate to 0. Cos t differentiates to negative sine t, so I get 2 sine t. Oh, sorry, that's it. That's dy dt. We're not going to do full dy dx yet. Dy dt is 2 sine t. Dx dt. If I differentiate this equation, this is like 2t minus 2 sine t. That's going to be 2 minus 2 cos t. So dy dx is going to be dy dt divided by dx dt. Dy dt is 2 times the sine of t. And dx dt is 2 minus 2 cos t. So we want to figure out where dy dx is equal to 0 and where dy dx is undefined. And we'll have to be a little bit careful because it's possible that those could happen. It's possible that one t value might appear to do both. So dy dx is equal to 0 if and only if 2 sine t divided by 2 minus 2 cos t is equal to 0. And this can only happen if the top is 0. So here the t values we get out, where is sine t equal to 0? Well, sine t is equal to 0 when t is 0. When t is equal to pi. When t is equal to 2 pi, 3 pi, 4 pi, any multiple of pi. And dy dx is undefined if the bottom is 0. 2 minus 2 cos t is equal to 0. Which happens if 2 is equal to 2 cos t. Which happens when cos t is equal to 1. So when is cosine of t equal to 1? Well, there's some overlap with this. This will happen if t is equal to 0. But not when t is pi, right? When t is pi, cos of pi is -1. But also when t is 2 pi. not 3 pi, cos of 3 pi is -1, but when t is equal to 4 pi, any even multiple of pi. So the first thing we observe is that we have horizontal tangent lines when dy dx is equal to 0. And this definitely happens when t is equal to the guys from this list, which are not in this list. So pi, 3 pi. And we might have vertical tangent lines. So definitely these, and maybe at the other ones, t equals 0, 2 pi, and 4 pi. We might have vertical tangent lines when dy dx is undefined, which looks like these would be at t equals 0, 2 pi, 4 pi. Now looking at the picture, horizontal tangent lines here and here. So these must be coming from those odd multiples of pi. This must be coming from t equals pi. This must be coming from t equals 3 pi. We suspect vertical tangent lines at 0, 2 pi, 4 pi. Remember, these are x values down here, not t values. So from the graph, we have maxes as our horizontal tangent lines, which come from pi and 3 pi. And those points are well, we would plug the t values into those equations. So if I plug pi in for t here, I get 2 pi minus 2 times pi minus the sine of pi. So let's see, x of pi comma y of pi. We get 2 pi for x. So when you plug pi in for t, you get 2 times pi minus sine of pi is 0. When you plug pi in for t here, what do you get? You get 2 times 1 minus cos of pi. Well, cos of pi is -1, so that's 1 minus -1, which is 2. So 2 times 2, which is 4. And x of 3 pi comma y of 3 pi. And if I plug 3 pi in for t here, I get 2 times 3 pi minus the sine of 3 pi. That's 2 times 3 pi, or 6 pi. And if we plug 3 pi in here, we get the same thing. We get 2 times 1 minus the cosine of 3 pi. Cosine of 3 pi is -1, so this is 4 again. So we have maxes at these points. The other t values where interesting stuff is happening are these even multiples of pi. And right now, we're not sure whether those are vertical tangents or horizontal tangents. But again, from the graph, we can infer that the other critical points are those vertical tangents, which must be the mins. Shoot paper so we can come back. We have mins at our vertical tangent lines, which occur when t is equal to 0, 2 pi, and 4 pi. And these points are, let's look at x of 0, comma y of 0. If you plug 0 in for t in the x equation, you get 2 times 0 minus the sign of 0. That's 0, right? 2 times 0. If you plug 0 in here, you get 2 times 1 minus the cosine of 0, where the cosine of 0 is 1. So this is 2 times 1 minus 1. This is the origin. The next point where we know there is a min is the point associated with t equals 2 pi. If I plug 2 pi in for t here, I get 2 times 2 pi minus the sine of 2 pi. Sine of 2 pi is 0. So that's 2 times 2 pi, which is 4 pi. And when you plug 2 pi in for t here, cosine of 2 pi is again 1. So this is 2 times 1 minus 1, which is also 0. And the last one was 4 pi. If you plug 4 pi in for t here, you get 2 times 4 pi minus 0, which is 8 pi. And if you plug 4 pi in here, cos of 4 pi is again 1, so that's 1 minus 1 is 0. So these are the points where we have mins. So we can label on our graph these mins and maxes. So mins, like we said, were 0, comma 0. Here's one of them. 4 pi, comma 0. Here's another one of them. And 8 pi, comma 0. The maxes, we said we're at the points 2 pi, comma 4. And 6 pi, comma 4. I'll give you a second to make sure your notes have these things. And I want to talk about why this works, make sure we're really comfortable with where this is coming from and what makes this different from what we were doing in Calc 1. The idea is this. Just like in Calc 1, dy dx gives you the slope of the tangent line. But here, because dy dx is calculated as dy dt over dx dt, because this thing is a function of t, not x, when we solve dy dt, or sorry, dy dx equals 0, we get t values out. Right? Like we got t equals 0, 2 pi, 4 pi for dy dx is undefined. We got t equals all the multiples of pi, 0, 2 pi, 3 pi, 4 pi, 5 pi, when we solve dy dt equals 0. So to find the points, on the curve, we must plug those t values back into the parametric equations. This example is a good kind of introduction to what we're going to do in section 10.2, which is all about doing calculus with parametric curves. I don't want to get too deep into that section now because I know you haven't had an opportunity to work any 10.1 homework. So I'm going to go ahead and stop here for today. I will open up your new homework set immediately after class. Please get in there and work as many problems from 10.1 as you can between now and Friday. That way you'll have level of comfort and familiarity with parametric curves that will allow us to start discussing how to do calculus with them without feeling overwhelmed. Next time, we're going to discuss how to come up with new parametrizations for a curve, how to reverse orientation, and then we're going to get kind of deep into the calculus stuff. So finding more mins and maxes, finding equations of tangent lines, finding areas. Most importantly, we're going to talk about something called arc length, which is the length of a curve. And that will lead to some very challenging integrals, which will be a lot of fun. But like I said, I do not want to dig into that stuff right now. I think it is best to give you a little bit of time to practice and breathe, and then we'll come to those things on Friday. Monday of next week, we're going to talk about surface area, which is kind of an extension of arc length. And it's going to involve thinking in the way that you thought when we did volumes at the beginning of the course. So you're going to take a curve and rotate it about some axis. But like I said, I don't want to get too far ahead of where you guys are in terms of homework. So I'll go ahead and end the meeting here. And then I'll ask you to please work as many 10.1 problems as you can between now and Friday. And then on Friday, we will dig a little deeper into doing stuff like this. Any burning questions for me before I let you guys go for the day? All right, then I will see you guys on Friday. Please take good care of yourselves. Look at the feedback I left on your exam too. If there is something missing, like I didn't get the work or something like that, please reach out to me as soon as you can so we can figure things out. I do not want anybody getting zeros on all of the free response problems just because you forgot to upload your work, but we do need to get that work and I do need to verify that it came from the day you took the test. That's it from me. I'll see you guys later.